Welcome to my channel Ganit Matrix. Here today we are going to discuss a concept, Euler's theorem for homogeneous functions. Here we will discuss the main concepts, and that is, first one is what is homogeneous function. Next, what is Euler's theorem? Euler's theorem for the first order partial derivative, so that is primary theorem. Next, and we will extend that theorem to second order partial derivatives, and we will discuss some specific formulas for non-homogeneous functions that can be transformed into homogeneous forms. And the practical utility of Euler's theorem involves in verifying partial differential equations involving trigonometric, logarithmic, and algebraic functions. Now, a function u equal to f of xy is classified as a homogeneous function of degree n if it can be expressed in the form u equal to x power n into f of y by x, where n is a real number. But to determine the degree, if u equal to function of three variables f of x comma y comma z, then f is said to be homogeneous function of degree n if f of xt, yt, zt equal to t power n into f of xyz. That is, our function u equal to f of xyz, and we replace the independent variable with multiple a factor t. That means replace x with xt, y with yt, and z with zt. It will be expressible. It will be expressible in the form t power n into f of xyz. Then this n is called degree of the homogeneous function, and this method is applicable to function of 2, 3 or more variables. So actually here we have discussed this is for 3 variables. If it is 2 variables, if u equal to f of xy is said to be homogeneous function of degree n if f of xt comma yt equal to t power n into f of xy. Now, if u is and this is the Euler's theorem for the function of 2 variables. If u is a homogeneous function of x and y in degree n, and remember that here u equal to f of xy, and f of xy is a homogeneous function of degree n, then according to Euler's theorem, the sum of the products of independent variables x and y and its partial derivatives equal to nu, right? X and y are independent variables, and the corresponding partial derivatives are dou u by dou x, dou u by dou y. So take the products of independent variables along with its partial derivatives, and take the sum x dou u by dou x plus y dou u by dou y equal to nu. What is this n here? This n is homogeneous function of degree n. N is the degree of the homogeneous function f of xy. Now for a function, now extend this to 3 variables. If u equal to f of xyz is a function, a homogeneous function of degree n, then x dou u by dou x plus y dou u by dou y plus z dou u by dou z equal to nu. Same here, n is degree of the homogeneous function. Now, this is all for first order partial derivatives, right? So extend this to second order partial derivatives. If u is a homogeneous function of degree n, then sum of its second order partial derivatives is governed by, see that, so this is the Euler's theorem for second order partial derivatives. right? And f of xy, u equal to f of xy is a homogeneous function of degree n. Then since this is second order partial derivatives with respect to x, dou square u by dou x square, and this is second order partial derivative with respect to y, dou square u by dou y square, right? And this is second order partial derivative with respect to x and y, and these are the products of independent variables and the corresponding second order partial derivatives, right? This sum equal to sum of the products of this independent variables x and y and the corresponding second order partial derivatives equal to n into n minus 1 into u. And same here, n is the degree of the homogeneous function f of xy. So in many cases, a function u is not itself is a homogeneous, but it is a function of u, like it is a function of some trigonometric functions, exponential or logarithmic functions, right? If u is not itself a homogeneous function, but it can be expressed in a function of u is homogeneous, right? If it can be expressed in function of u, it can become homogeneous. Then for the first order, then in that case we will use another theorem. So what is that? If f of u, right, since u is itself not itself homogeneous, but it can be expressed as a function of u equal to f of u, and if that f of u is homogeneous function of degree n, then x dou u by dou x plus y dou u by dou y equal to what is that? N is degree of the homogeneous function multiplied by f of u by f dash of u. F dash of u means the first derivative of f of u. Similarly, same this applied to if u is not itself a homogeneous function, then for the second order partial derivatives, this theorem is x square dou square u by dou x square plus 2xy dou square u by dou x into dou y plus y square dou square u by dou y square equal to g of u into g dash of u minus 1, where this g of u equal to n times f of u by f dash of u, right? And where we applied here, where we obtained this is obtained from the first order Euler's theorem of first order partial derivatives. From here, n times g of u equal to n times f of u by f dash of u. So we will just discuss this, right? We will just discuss these non-homogeneous transformations, right? And here, and remember that here the function u is not itself homogeneous, right? So here, what is u here? U equal to, consider this is inverse trigonometric function, u equal to secant inverse of x cube plus y cube, because this is a non-linear term, secant inverse trigonometric function. Here sine inverse, this is the non-linear term, logarithmic, log of x square plus y square plus z square, non-linear. Or if you observe that, what is that? If you observe that these are composite functions, right? These are composite functions. I am talking about logarithm, the first one, second one, third one, and fourth one. These are the composite functions. That means function of a function. These are the composite ones. Secant inverse is the outer function and the inner function is the algebraic function. Similarly here sine inverse outer, the inner one is some algebraic function. Similarly here the third one and fourth one also. So if u equal to secant inverse of x cube plus y cube, right, then what we make this? We can express this u as a function of u. This is the transformation, right? Since u equal to secant inverse of x cube plus y cube by x plus y, right? Now apply secant on both sides, then secant u equal to x cube plus y cube by x plus y, right? So here we are getting f of xy. Here we are getting f of xy. What is that f of xy? X cube plus y cube by x plus y, right? So what we get? secant u equal to x cube plus y cube by x plus y, which is f of xy, right? Now, how to find the degree? Replace t with tx, replace x with tx and y with ty. Then x cube becomes t cube x cube plus y cube becomes t cube y cube by tx plus ty. Now at the numerator part, take t cube common, at the denominator part t common, right? So t cube into x cube plus y cube by t into x plus y. T cancel. Now the numerator t square into what it becomes f of xy. T square into f of xy. That means t square, right? So the degree is 2. Degree is 2. Degree is 2. Then the resultant g of u, that means the final answer, the final result. So what is that? Right here, since u itself is not homogeneous, then we will apply this theorem. If f of u is, since secant u is homogeneous function, right? Secant u equal to x cube plus y cube by x plus y, which is f of xy and which is homogeneous function of degree 2. Then what? X dou u by dou x plus y dou u by dou equal to n times f of u by f dash of u. N is what? N is what? N is degree. N is degree, degree 2. What is f of u? Secant u. So 2 times secant u divided by what we write in the denominator term? Derivative of secant u, right? Derivative of secant u is secant u tan u. Secant u cancel, right? 2 into 1 by tan u, 1 by tan u cot u. So we'll get 2 cot u. So in this way, we will do all these problems. So, and this main thing, since the functions involving tan inverse, that means inverse trigonometric functions, and if it is for second order partial derivatives, then it can be expressed in the form g of u into g dash of u minus 1. And in the next video, we will discuss the problems on Euler's theorem. Thank you.